In statistics, it's quite common to take a sample and use that sample to estimate what's happening with the entire population. That's what we're going to do as we create a confidence interval for the mean when the standard deviation of the population is known. But first, what is a confidence interval? When we're saying we want a confidence interval, what we mean is our sample mean is being used to estimate the population mean. However, this estimate's never perfect because we didn't sample everyone. There's some error between our sample and the population mean. So what we're going to do is we're going to give a range for the possible location of the sample mean. We'll get that range by subtracting the error from our sample and adding the error to our sample mean. And we can be confident that our population mean is probably going to fall between those two numbers. Let's look at how we can actually build that confidence interval. First thing we need to know about is what's called critical values. These critical values are the numbers such that the area under the standard curve between negative z sub c and positive z sub c is equal to c, or that confidence level. So what we mean visually by this with a picture is if we have our normal curve, we want c, whatever that area is, whatever that probability is, whatever that confidence is, to be in the middle. We want c in the middle. That means there's a little bit left on the outside on both the left and right side. So if c is in the middle, we'll have what's called alpha, which is the area on the outside. To calculate that, if 1.0 represents all the area, 1 minus c will give us the alpha. And then, to find that z sub c, z sub negative c, and z sub c, we're going to be most interested in this left tail because that's what our tables in Excel will give us. And so we need to take that alpha, which is in both tails, and divide by 2 to get the left tail. So this area is alpha divided by 2. Once we know what alpha divided by 2 is, then we can use the inverse normal function to calculate our z sub c. However, it's important to note with confidence intervals, we can never know for sure how accurate our estimate is of the actual population mean. So to estimate the error between our sample mean and the population mean, it's going to depend on how confident we want to be, that z sub c value. The way we calculate the error is it's equal to z sub c times the standard deviation divided by the square root of the sample size. And the more confident we want to be, the larger error we need to account for to make sure that actual mean is included in our confidence interval. So let's take a look at an example. Let's say a jogger knows that the standard deviation of her daily run is about 1.8 minutes. For her past 90 runs, her average time was 15.6 minutes. We're going to find a 95% confidence interval for the true mean of all of her runs. First, let's draw a picture of what we're talking about. So we want a 95% confidence interval. That means we want 0.95 in the center of our normal curve, which means the alpha in the tail is 1 minus 0.95, which is 0.05. And for one tail, we divide that 0.5 by 2, the 0.05 by 2, to get 0.025. We want that left tail to have an area of 0.025. We already know the area. We need to find the z sub c's that go with it. For that, we're going to go to Excel. We want our alpha divided by 2 to be 0.025. So we'll say equals norm.s.inverse, and then type in that probability of 0.025. And it's going to give us the z value, let's round to 2 decimal digits, of 1.96. So the negative z value was negative 1.96. The positive z value then is positive 1.96. That's our confidence value, our critical value for a 95% confidence interval. Now we're ready to see what kind of error we're dealing with. How far off is our sample mean from the actual mean at the 95% confidence level? That's the z sub c times our sigma divided by the square root of n. Z sub c we found out was 1.96 times the standard deviation of her runs is 1.8 divided by the square root of the sample size. She did 90 runs. And so we can do that on our calculator. 1.96 times 1.8 divided by the square root of 90 gives us an error of 0.37. Let's round to 2 decimal digits. So that means our average time of 15.6 is off by up to 0.37. So to make my confidence interval, we're first going to take that 15.6 and subtract the error to see our lower bound. And then we'll take the 15.6 and add the error to get our upper bound. When we do that, 15.6 minus 0.37 is 15.23. And 15.6 plus 0.37 is 15.97. And then we can say with 95% confidence, or that we're 95% confident, that the true mean of her run times is between 15.23 and 15.97 minutes. Let's find a 99% confidence interval for the true mean of her runs. We want to be more confident, so we need to account for a larger error to make sure we capture the actual mean. So let's again draw a picture to get started, following much the same procedure. But this time we want 99% or 0.99 in the middle, which means alpha, the tails, is 1 minus 0.99, or 0.01, which means each tail individually, dividing by 2, is 0.01 divided by 2 is 0.005. That is the area in the left tail. We can use the inverse to find our z sub c values. We want alpha over 2 to be 0.005. We'll say equals norm.s.inverse because we have the probability of 0.005. We just want to know what z goes with that. It's going to be negative 0.25. Let's go 3 digits here. Negative 0.2576. 2.576 is going to be our z sub c. So our error is equal to 2.576 times the standard deviation of 1.8 divided by the square root of the sample size of 90. And when we do that on our calculator, 2.576 times 1.8 divided by the square root of 90, we end up with an error this time of 0.49 when we round. So our confidence interval is going to be our mean of 15.6 minus the error of 0.49 gives us a low value of 15.11 and a high value, taking 15.6 plus 0.49, of 16.09. So we know now with 99% confidence, we believe the true mean of all of her runs is going to fall between 15.11 and 16.09. Here we focused mainly on the calculation of finding that confidence interval, but I want to look at a visual of what a confidence interval really means. If we do a 95% confidence interval, that comes out to 19 out of 20, 95%. A 95% confidence interval indicates that 19 out of 20 of the samples from the same population will produce a confidence interval that actually contains the population parameter. In other words, if I did this 20 different times, I took 20 different samples and found the confidence interval for all 20 of them, 19 would contain the actual mean, that 19 blue bars here. One of them missed it by just a little bit, and that means we're 95% confident that we're going to capture the mean 95% of the time. 99% confident would mean if there were 100 bars, 99 of them would cross that actual mean, and 1 bar would be outside of the actual mean. Often we're interested in accomplishing a specific error. We want to be within maybe 1 unit or maybe half a unit. If we want to get a specific error, the way we can address that is we find what the minimum sample size is. Because the larger the sample size, the smaller our error is going to be. The formula to calculate the minimum sample size to get the confidence level we want is z sub c times sigma divided by the error squared. Here's how that works in an example. Salmon have a standard deviation in their weight of 2.15 pounds. We want to be 90% confident that the sample mean of a group of sample we take is within 0.20 pounds of the true mean. In other words, it's not a very straight line, but that's okay. We want to be 90% confident, have 0.90 in the middle, which means we want alpha to be 1 minus 0.90 in the tails of 0.10. Each tail divided by 2 is 0.10 divided by 2, or 0.05. We want to have 0.05 in the tail. So we'll use Excel to find our negative z sub c and our z sub c that give us that situation. To get that, we'll say equals norm dot standard dot inverse. We want an area of 0.05. And we get negative 1.64. That means our z sub c is 1.64. And we're ready to calculate the minimum sample size using that formula. The formula says we take our z sub c, which is 1.64, times the standard deviation of 2.15, divided by the error. We want to be within 0.2 pounds of the true mean. So that means we want an error of 0.2 squared, and typing this into our calculator should give us the minimum sample size that we need to get within 0.2 of the actual mean. So 1.64 times 2.15 divided by 0.2, and then we take that number and we square it, we'll end up with 310.81. Similar to when we calculated bin widths with histograms, we always want to round up. This time we do round up naturally, but we need at least 311 salmon so that our confidence interval makes our mean fall within 0.2 of the true mean. So hopefully this video was helpful as you create confidence intervals for the mean when we know the standard deviation of the population. Good luck to you as you practice with that.